Hey guys, today's day 5. I wanted to start today by looking at a couple of the problems from last time. I feel like I didn't get enough examples done, and so I don't ever want to feel that way whenever I come to a class, because if we were in the normal classroom setting, you'd have the opportunity to say, hey, could we maybe spend some time reviewing these kinds of things, because we didn't seem to get it last time. And so I wanted to make sure to spend some time. We'll go through 3 of the problems from last time. That'll shorten your homework assignment a little bit, which is nice. And we'll use it to discuss some of the properties from last time and see how they fit together, and we'll even showcase a few ways that you can do problems a little differently. And then afterwards, we're going to discuss scientific notation, because scientific notation is kind of like in the same category in terms of how you're supposed to use it. And if we finish that, we'll have our homework assignment tonight. If we don't, then I'll assign the scientific notation homework tomorrow instead. Since I've got some grades in, I've had some people already asking questions. Yes, if you wish to send in like reworks on problems, so if you missed certain problems that I mentioned and you're like, hey, can I get a second chance? I'm more than fine with that. Just shoot me an email with the information you have, and I'll see what I can do. It's more than happy to do that kind of stuff as long as I get it. It may take some time for me to grade, but it will happen. So just let me know. And speaking of grades for those that submitted via Blackboard should all be updated. I didn't remember until this morning that I had a bunch that were sent via email, so I will update those as well today. And so all grades should be fully updated today, which should be great. Let's go ahead and get started. We're going to look at a couple problems from our previous homework assignment and kind of showcase how we can use some rules and properties to kind of get those answers. I picked 3 that appeared to have a good mix of different properties, 28, 30, and 40. Let's look at 28. 28 has the following statement. We have x to the negative third over y squared to the negative fifth power. Okay. There's a question in these kinds of problems of which path do we want to go. So let me showcase kind of the 2 big thoughts that could happen first. We could simplify the x to the negative third power first. That's a possibility. We could also simplify the negative fifth power on the outside by distributing. And there's even a third property. We could just do all the negatives all at once. And so I'm going to showcase this problem in 3 different ways and show how they eventually all get the same answer and all use specific properties from last time. So let's start with this first way. I simplify x to the negative third power. So I'm going to do that up here as option number 1. If I simplify x to the negative third power, remember what negative third powers do. What negative third powers do is if it's on top of the fraction, it will send it to the bottom of the fraction, meaning that it will take that function and be rewritten as 1 over x to the third y squared to the negative fifth power. Notice that the negative power of the x caused it to go to the bottom of the fraction. We can't leave the top blank, which is why there's a 1 there, because remember, if there isn't something, it's always a 1. It's a hidden 1, but it's there. And that can work on either the top or the bottom. But you can always have a 1 there. That was actually one of our properties called the identity property. And so we can take that negative third power and bring it to the bottom, and that works. Now from here I have different options, but I'm going to go with the most common. The most common would then be to distribute this negative 5 power. Now watch what happens when I do that. So I have to distribute to every single term, so I have to distribute that as a 1 to the negative fifth power, x to the negative 15th power, y to the negative 10th power. So let's talk about what happens. First of all, x to the negative, or 1 to the negative fifth power up here, 1 to any power is 1. It's just a property of numbers that you should know. And so on top, this is really just 1. And now we can see we have negative powers in the denominator. Now, remember, negative powers cause a flip to occur, meaning if they're on top, they go to the bottom, which is what we did for our first step. But there's a cool thing that happens. If they're already on bottom, they can actually go to the top, meaning that this statement becomes x to the 15th, y to the 10th. Notice that in this case, my x is to the 15th power. That's a positive power My y is the 10th power. That is a positive power. All powers are positive. The 1 is absorbed because 1 times anything doesn't change anything. And so this statement is the answer. And it matches all of our rules. Now, what if I had decided to deal with the negative 5th power first? Well, watch what happens. This is option number 2. I have to distribute the negative 5 power to each term, so it'd become x. Negative 3 times negative 5 would become positive 15. 2 times negative 5 would become negative 10, so negative 10 power. Notice the negative 5 affects the power, not the variable. Okay? It's still just x. It's not become negative x. It's still just y. It didn't become negative y. It affects the power, nothing else. And now from here, we can take our next step, which is, well, negative powers cause a flip to occur, so this negative 10 on bottom can move to the top, meaning we get x to the 15th, y to the 10th. Notice it's the exact same thing. Now this one's a little bit shorter, and some would argue a little bit easier, but you can't tell that from the beginning unless you practice, unless you try these problems out and see how they're going to work. Now, there's a third option. This option's more advanced. If you're in the more advanced stage, and you're like, hey, this is really easy, can you show me a better way? Allow me to show you a way to do this using the negative powers and negative properties to fix this. So, what's a negative power actually do? Remember, negative powers flip. What that means is, if it's a over b to a negative power, you can write it as b over a to a positive power. It flips everything. Meaning if a was on top, we can put it on bottom and change the power to positive. If b was on bottom, we can move it to the top and change the power to positive. And this always works, even if you distribute. So if you have a to the negative c over b to the negative c, we write this as b to the c over a to the c. Notice that the a went to the bottom and became a positive power. The b went to the top and became a positive power. This always works. Negative powers flip on the fraction. And if there isn't a fraction, make it a fraction, which you can always do. So watch what I can do with this statement by fixing the negative power on the outside. I can make this become y squared over x to the negative third, but with a positive 5 power. These two are equivalent, because it's just this property right here. I take the negative power, and it causes the inside to flip and the power to become positive. So the inside flips, x to the negative third goes to the bottom, y squared goes to the top, and the top becomes a 5. And I know it works because if I continue going, I get the same answer. I just distribute the 5, so it becomes y to the 10th over x to the negative 15th, and that negative 15th power would go to the top, becoming x to the 15th, y to the 10th, which tells me that it worked. I made good choices. So in this kind of problem, note that the different ways you can approach it and how you can get the solution really can affect how we get to the answer. Let's now look at 30. Okay, number 30. We have w to the 0 power, x to the negative 5th power. Oh, no, sorry. That should be x to the positive 5th power, all to the negative 1st power. Okay, let's watch what happens. There are two good ways to do this problem. I could use the property to, or I guess technically, once again, there's 3. I could use the property to get rid of the 0 power. I could use the distributive property to simplify that instead. Or I could use the negative property to flip this thing over. Let's showcase all 3 real quick. Okay, option 1. Let's show what happens if I deal with the 0 power. Well, if I deal with the 0 power, remember, anything with a 0 power is 1, meaning this statement becomes 1 times x to the 5th to the negative 1st power. From there, I can take my next step, which would be to distribute that negative 1. 1 times anything will cause this 1 to disappear. X to the 5th, we would distribute the negative, so that becomes x to the negative 5th. And because it's negative power, I can use my negative power rule to drop it to the bottom, become x to the positive 5th. This is one way to do it, where I simplify the 0 first. Alternatively, instead of doing that version, I could choose to distribute first. Now when I distribute, I would get w to the 0 power, because remember, -1 times 0 is going to be 0, because anything times 0 is 0. And then x to the 5th times -1 would become x to the -5th. And from here, whichever ones I choose to do, w to the 0 power becomes a 1. X to the -5th power becomes x to the +5th as long as it's on the bottom. And so again, we get the exact same solution. It doesn't change the solution, it just changes how we get there. Notice that this means that your order of operations is more flexible. I don't have to do the power first. I don't have to simplify first in this example, provided that I use all my properties correctly. And the last thing I can do with that negative. Well, what does a negative power do? Well, according to this, a negative power causes the thing to flip over. Now, this isn't currently in a fraction, but remember, it is. You can always put a number over 1 and not change the solution, which means that this becomes 1 over w to the 0 x to the 5th to the +1st power. Then remember that a power of 1 is essentially nothing. And then a power of 0 becomes 1, meaning I end up with 1 over x to the 5th. Look at that. We get the same answer no matter what we do. And it's an important detail. Because of how these functions work, because of how these rules work, you can take many different paths to get to your solution, but we should all agree that this is the same solution for all of them. That is the point of these properties, is that we should all agree that this is the solution no matter which path we take, because that's how the properties work. Let's look at our last one, number 40. Number 40 has m a to the 6th squared times 1 over m cubed a squared. Now, because of how this one is written, there's actually only a couple things we can fix up front. And so, I cannot put these two together because it has a power. And remember, order of operations says we should try to do exponents first if we can. And so I should try to take this 2 and distribute if we can. Now, up above, this didn't matter as much. It just didn't. But here it does. That's why order of operations is so essential to know well. It's because you can always use order of operation to get the answer, whereas sometimes you can get around it, but you can always use it in the correct way this time. So, this one, the only path we can really take is get rid of that square. So, let's do that. So this would become, let's see, m squared a to the 12th times 1 over m cubed a squared. Now, from here, let's remind ourselves, remember, the m, it has a power of 1. That's one of our properties, the identity property for powers. So, we take 2 times 1 to get 2, 6 times 2 to get 12. Now, from here, we can take these two terms and combine them because they're being multiplied. We take top times top, and bottom times bottom. This would give us m squared a to the 12th over m cubed a squared. Now, from here, we can use our property of the quotient, which is the division property, which states that I can take these two m's, one on top, one on bottom, and I just subtract the powers. This would be 2 minus 3, and this would be a 12 minus 2. From there, we simplify. 2 minus 3 would be the negative first power. 12 minus 2 would be 10. And from here, we have to remember that you're not allowed to leave it with negative powers, which means we can use the negative power rule to make that negative power drop to the bottom of the fraction. Because remember, there's always a fraction here. It's always over 1. And so this becomes a to the 10th over m to the 1st, or just a to the 10th over m, which is the preferred way. In this case, if you don't distribute first, there's a good chance that you make a mistake here. Because if you don't distribute first, you're going to try to cancel using some of our other properties. Those other properties are multiplication and division, not supposed to be done first. You're supposed to do powers first. You can get around it sometimes. There are sometimes cases where you can go outside of order of operations. But in general, order of operations is the best way to go. So there's 3 problems that you no longer have in your homework assignment because we did them together. Let's take a look at today's material. For today, we're talking about scientific notation. Now, if you haven't seen scientific notation before, I'm sorry, let's talk about it. So what is scientific notation? Before I talk about scientific notation, I want to reference something about why it's called scientific notation and why it's so useful in terms of real world. If you like science, you might have heard of something called the Andromeda Galaxy. The Andromeda Galaxy is the closest galaxy to our own Milky Way galaxy. Even so, at the closest distance, the distance from the Andromeda Galaxy to Earth is the following number. It is 24 with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Oh my lord. 13, 14, 15, 16, 17, 18, 19, 20, 21. Yeah, meters. It is a 24 with 21 zeros after it. Now imagine trying to do math with this number. Like imagine trying to multiply this by 16. Or trying to do the math with this kind of problem with such a large value. And like this is not even that big compared to like other numbers in mathematics. Like the next closest galaxy is a few thousand times. It's got a few more zeros after it. And that makes this number very, very, very big. And it makes it very unwieldy. So what scientific notation says is we can take this number and rewrite it using some very specific rules. So in scientific notation, a number is rewritten in the form a times 10 to the nth, where in this case our value is between 1 and 10. And n is an integer. Meaning, rather than writing this as 24 with all these different things, there's an easier way to write it. This is actually 2.4 times 10 to the 22nd power. This is much easier to see. It's much easier to write, for sure. I don't want to have to write that again, ever in my life. This is much nicer to deal with. And notice that it contains the same information if you were to multiply this back out. Because remember, 10 to the 22nd would just mean the number 10 written 22 times. And 2.4 times the number 10 written 22 times will end up being this number. You can take a calculator out and test this. Although most calculators can't actually work with this number because it's simply too big. It will try to immediately convert it into this form. And so this is scientific notation. It's a much easier way to write it, and it's easy to make comparisons. Because, for example, if I write the number of, for example, the number of stars in Andromeda's galaxy. Now, this is an estimation, but even so, you can look it up online. This is the number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. This number is a big number, but we can write it much simpler in scientific notation as 1 times 10 to the 12th power. And so when it's written this way, it's much easier to see, what's the difference between them. Well, this is, 10 to the 12th versus this 10 to the 22nd. There's a full factor of 10 difference between these two. And so this is scientific notation. Now, it's also used with really small numbers. For example, I was in Boy Scouts. I loved being in Boy Scouts. And we always talked about lightning. lightning is really dangerous when you're in Scouts, because if you're camping and stuff, you can't always get to safety. However, there's something you should know. The probability of getting struck by lightning is this number: 0.0000143. That is a very small number. Like so small that you couldn't measure this on a ruler. If you wanted to measure it on, in terms of like, if you're talking about a mile, this is, an inch or two. This is a very, very tiny number. But in scientific notation, this number is a little bit easier to put into scale. We write it as 1.43 times 10 to the 6th. Now notice a couple things about scientific notation. If n is bigger than 0, so in other words, if n is positive, that means your number is large. If n is less than 0, it means your number is very small. So you can see here how this is a very tiny, 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 tiny number, but this is rather large. And so it has a number bigger than 0, 22 is bigger than 0, whereas this is a number that is less than 0, it's -6. And so it's a very small number by comparison. And so anytime we talk about scientific notation, you can easily make that check to say, oh, how is it related to the other one? Well, just look at the number on the n. And the number of the n is super important, because if it's a +6 instead of a -6, that means it's a 1.43 with 6 zeros as opposed to 1.43 with 6 decimal places. So then the question becomes, how do we write this? Well, it's actually pretty straightforward. Let's look at one more. Here's a nice, interesting one. As of April, the world population was 715800000. Now, when we write in scientific notation, do note that there are a bunch of these that are equivalent. For example, if I wrote 715812312 times 10 to the first, these two are actually the same thing. Because if I take this times 10, we'd move this one place over, and we end up with the exact same equation. Similarly, let's say we did 7158, we could do it 10 to the 6th, where I take these 6 zeros and turn them into a power of 6. But notice that this doesn't meet the first or the second part of our definition. The first number, the number that is away from our answer, needs to be between 1 and 10. This number is not between 1 and 10. It's much bigger than 10. And so this is not quite right. And so in scientific notation, we write this number as 7.158 times 10 to the 9th power. And the easy way to get that number, n, is just how many decimal places. So there's 3, 6, 9. So there's 9 decimal places to the right of 7. So it's 9 decimal places, therefore it's the 9th power. It's an easy trick you can use to always be able to write in scientific notation. Similarly, if I was to take a number like the odds of winning the lottery. Not a very nice number, I'm ashamed to say. 0.1, 2, 3, 4, 5, 6, 7, 8, 7, 1, 5. Oh my gosh. Okay. We can write this in scientific notation by doing a simple counting technique. We count 1, 2, 3, 4, 5, 6, 7, 8, 9. This means there are 9 between the decimal point and our first number that is between 1 and 10. So the zeros don't You don't stop at 0. You stop when you get your first number, and you go past your first number. So 0.1, 2, 3, 4, 5, 6, 7, 8, 9. This would tell me that the solution is 7.15. So just we keep the same three numbers, 7.15 times 10. Since it's a small number, it would be the negative ninth. And so the odds of winning the lottery in scientific notation would be 7.15 times 10 to the negative ninth. The odds of winning of the world population of choosing a person at random, that'd be 7.158 times 10 to the ninth. So notice the difference between these two values. They are very close together. Basically, it's one in the entire population of the Earth. But notice that this number is very large, so it's a positive 9. This number is very small, so it's a negative 9. And you can always count your way to the answer. So if we look up here, if we wanted to figure out why it's 22, we'll have to start after the first number between 1 and 10. The first number between 1 and 10 is the 2. So we count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. There are 22 zeros, and that's why we have a 22 on the power. In this example, we count 1 is between 1 and 10. Oh my gosh. You can include 1 in this list, so we should make sure to have that listed. But you cannot include 10. And so, we start here. Count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And that's why, since there are 12 places between the 1 and our decimal, we count as 1 times 10 to the 12th. And same thing here. 1, 2, 3, 4, 5, 6. Our first number is a 1. And so that's why it's 1.43 times 10 to the negative 6th. Now, it should be noted these two are the same. Because if I was to take 10.43 times 10 to the negative 7th, it's the same number. What should be noted is it doesn't match this rule. The rule is this first number needs to be between 1 and 10, and it can include 1, but it cannot include 10. This is bigger than 10. 10.43 is in fact bigger than 10. Crazy idea, right? So we know this is not right. This is like true, but not scientific notation. In other words, what happened here is the example where I'm an idiot. Expect 14.3. Duh, dude. Tuesdays. If I went one step too far, like if I, instead of stopping at the 1, I stopped at the 4. And if I did, then I'd have 7 places that I skipped. And so that's why it's a negative 7. But while this may be true, like 14.3 times 10 to the negative 7th is this number, if you actually type this in a calculator, this number will pop out. It's just not in scientific notation. Scientific notation requires it to be in this particular form. So, that is the main detail. You also need to make sure that you're prepared to go the other way if necessary, which is in fact pretty simple. Let's look at a couple of numbers that are written in scientific notation. Example. In this case, let's look at 3.547 times 10 to the 14th. What this means is you can write it in what's referred to as standard notation, which is, the big long form. These numbers are all written in standard notation. These are standard. This is in scientific. How do I write it backwards? The 14, if n is greater than 0, that means the decimal moves to the right. If n is less than 0, it means the decimal moves to the left. In this case, I have 10 to the 14th. So I'm going to take this 3, 5, 4, 7. I'm going to move the decimal place 14 spaces to the right. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. This is 3, 5, 4, 7, 0, 0, 0, 0, 0, 0. This is why we use scientific notation. It's much better. Much easier, that's for sure. Alright, so these two numbers are equivalent. And again, if we were to convert backwards, we could get that answer by just taking this and being like, okay, how many zeros is it? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. You need to be equipped to go both ways, because in mathematics, it's always available to go both directions. We'll continue the conversation about scientific notation next time, specifically how to do operations with it. And so for tonight, there will be no homework. That'll leave us off today. Look forward to seeing you guys tomorrow. We'll discuss more you can do with scientific notation, and I'll see you guys then.